Hey guys, what's up? Eddie Alho here with KissAnalog.com. Today I got kind of an oscilloscope tutorial, maybe a learning thing on oscilloscopes. Okay guys, so digital oscilloscopes. You know, a lot of you guys maybe have only used digitals, or maybe a lot of you guys use analogs and you're just starting to get used to digitals. Well, digitals scopes have come a long ways. I'm a totally fan of digital scopes nowadays, where, you know, being an audio kind of guy, doing audio designs, and then being a power supply guy for all my years as a professional, I've always liked, you know, back in the day, I was a big Tektronix analog fan, and I got my first digital scope, pretty expensive, but I got a really good deal on it. But anyway, yeah, wasn't so great. The inexpensive scopes today kick its butt. It was an expensive Tektronix scope. I think even used back then it was like $3 or something, many years ago. 2430, if you guys remember that scope. Anyway, I had a 2465, 2430, thought I had the world. But anyway, now scopes come a long ways. And what they've done is well, we all are familiar with the Nyquist theory, I think. You know, you have to have 2 samples per cycle. Actually, most scopes are designed for 2.5 cycles per second, because you want a little bit more than 2. In theory, 2 sounds good, but you need a little bit more, because you can actually have each sample on each crossing point, which would always be 0, so that doesn't work. You need 2 samples per cycle, but they can't be on the 0 point. So 2.5 cycles takes care of that. Anyway, that's that thing. That takes care of part of the problem for the horizontal picture. The other thing is catching enough samples and have a deep enough memory to capture something, maybe some noise that happened over here, capturing a whole bunch of cycles so you can zoom in on, hey, there's something that looks funny there, I'm going to zoom in on that. So having that deep memory really, you know, makes digital scopes useful. And then also the refresh rate, you know, how they're so fast now. So anyway, that part I think we all have a pretty good understanding of. The other thing is the vertical scale, the amplitude, the voltage or current, whatever you're measuring. It's 8 bits for most scopes. I would say most scopes under a few thousand, even 3, if you're talking brand names, anywhere from 2 to 5,000, they're all going to be 8 bits, okay? Or in those brand names, you might get 10 bits, and you might even spend 10 grand for 10 bits, you know? But there are a couple. Roden Schwartz came out with one, and the Roden Schwartz one I think is like 10 bits, and it's a few thousand or something like that. But now some of us are familiar with OWON. OWON's kind of a newer brand, and you know, technically it's a great scope. This firmware needs a little work, especially around the FFT, but otherwise, except for the FFT portion, and the FFT is starting to come around, but the scope is a great scope. Beautiful screen, and it's 14 bits. I got one that's 14 bits. I'm going to show you, compared to my GW Instek, which is 8-bit, which, by the way, there's some people that feel like they're 10 or 12 bits. I checked in with GW just to make sure. As far as they know, they're all 8-bit, which is kind of funny because you think they would just know for sure. But maybe there's some early models that were higher, they put higher analog. I think the thing is, well, what I was going to say is maybe some of the early models before mine came in as 12 bits, but I doubt it because it takes a lot of design work to get 12-bit. I don't think you'd go backwards unless it was just not working well. So the vertical thing is 8 bits. That's 256 slices. So you take that whole window. Now your waveform might only be taking up half of it. So 256, if your waveform's only half the screen, you only get half that. So it's, what is that, 256? What is that, 128? Something like that. So you get like 100 128 slices. I did some math. Okay, so the math. If you filled the screen so that you're using top to bottom, 256 slices would be 39 millivolts per slice. So you'd have 39 millivolts. And what it would look like is a staircase. You'd go up 39 millivolts, staircase, up 39 millivolts, staircase to the next sample. So every sample, you would go up 39 millivolts, sample, up 39 millivolts. Now to the naked eye, when you zoom out, it looks great. But when you zoom in, so let's say you're looking at audio signal, right? And you want to look at crossover distortion. So you capture, some signals, and then you zoom in to that. You're going to see, you might see those chunky steps, okay? The 10-bit one, like the Roland Schwartz, 1024. So it's 4x. So every time you go, it's 2 to the 8th power, or 2 to the 10th power, you go 4x, okay? So 2 to the 12th power, another 4x from 2 to the 10. So you go 4096, okay? And that's 2.44 millivolts. So I have a Picoscope. I don't have it right here on my bench. I do have this 5555 here, okay? But I have the 4444, it's 4444, 4 fours. That one is all differential inputs, and that one's, it's 12 bits, but it can go up to 14, okay? That's pretty crazy. And this 5000 starts off at 8, but you can go up to 16, which is 152 microvolts steps. Now that is some resolution. So that's what I want to show you, is that vertical resolution. So we're going to come over here right now. I got this Class D amplifier, and I'm just going to turn it on. And what's going to happen is this thing gets powered up. The Class D operation, it's like a switching power supply. It runs at, let's say, 400, 500 kilohertz, okay? And it's just sampling. And so we're going to see this sampling noise. You can't hear that. 400 or 500 kilohertz, you can't hear it. But you'll see, but on the scope, we can pick that up and we can see this, it's an LC filtered square wave. So we'll see a sine wave. And we'll see the frequency, okay? And then we'll zoom in on that and we'll see, what it looks like, all right? So this will be fun. Let's do it. Oh, and by the way, I'm going to use the GW Instek. I'm going to use this Mixig, which I love this scope. And I'm going to use this Pico, which I've become a huge Pico fan. So let's take a look, see what you think. Oh, and you know what? I think I'm going to bring on the OWON. It's in a box somewhere. I'm going to pull out the OWON. We're going to take a look at that, okay? Pretty nice scope. Nice, beautiful screen, touch screen. Anyway, this is touch screen as well. I'm going to try stay away from touch screens and just make this simple. Let's do it. Okay, guys, we got this new Micsig here. It's really shiny, reflective screen. Sorry about that. I love this scope, but let me tell you what we're looking at. We're looking at the Class D oscillation, the frequency. Let me get some more cycles. This is the Class D sampling. There's no signal right now. I just have it turned on. We're looking at the output. So we're just kind of seeing basically the noise, the high frequency noise. Here, I'm going to get some measurements down here. Let's turn off these two. And let's turn on frequency and RMS. Where is RMS? There it is. Okay, so we got about 1 volt RMS and about just over 500 kilohertz. Okay, I'll freeze that. So that's our image. It just happens to be, if I try to expand this more, it will, if I try to expand that more, it goes to 200 milliamps. It's off the screen. It's kind of funny here. Let me see this. I have it set at current because I had a current probe. It's AC coupled, 10x, 20 meg bandwidth limit. Okay, I think I have all the scopes set up this way. So let's go back to this, and we're going to go to 500 millivolts. which we're not using the full screen. So we're not getting the full, you know, benefit of the A to D. But let's just see what we do see. Now, if I start, so I froze the screen. If I zoom in on this to try to look at the crossover point real, okay, I'll go to 10 millivolts, okay. Now let me spread this out. Okay, I'm gonna put the frequency right here, the crossover right here. So then I'll stretch it out around there. Okay, that's a falling edge, I guess. But look at that. So we have these chunks. It goes from here to here to here. This is 10 millivolts per division. So like 20 millivolts. A little bit more than 20 millivolt chunks, right? So that seems like, you know, it's turned out this way because I'm not using the full screen. These are little 20 millimeter chunks or steps. That's that ladder. And see, it's kind of noisy in between here. Let me see if I can improve on that. We'll go back to, let's go back to 500 millivolts. Sorry, it's kind of hard because I'm trying not to get in the camera, and anyway, it's so okay. Well, look at those cycles. This is 14K, all right? So it's not a very fast sampling rate. So let's just see if we improve on that, if it helps. What we're going to do is, it was on auto. I'm going to go up here to the max. Let's go back to screen. Have turn this on so to reset. So now it's 70 meg. So now let's freeze that again, and let's see if we get anything better. Okay, we're going to zoom in again. All the way, okay, we're going to go to all the way to 10 millivolts. Yep, that's as close as I can get. And then we'll stretch it out again. Let me move this over. Yeah, it's about the same. It's kind of, so look at this. We're 2 nanoseconds. So for about 4 nanoseconds, it's just a block. That's kind of interesting too, right? So 4 nanoseconds is just a little block. There we go. I just wanted to see how many cycles it did in auto. I'm going to do less cycles to see if we get any better resolution, okay? So we'll try that. And I'm going to get rid of the cursors. We don't need those on. Okay, so, alright, so there we are. We got basically 1 cycle. So let's freeze that. And let's zoom in on that. Down to 10 millivolts. And let's go to that 2 nanoseconds again, maybe. Alright, there's 2 nanoseconds again. This time we're getting on the rising edge. And it's about 2 grids. It's about 4 nanosecond chunk again. And about 40 millivolts chunk vertically. So that's the staircase pattern. Yeah, so that's the staircase. That's what I'm talking about with an 8-bit scope. Okay, let's go look at another scope. All right, so just before we do, I just decided to turn this on running. So when we're actually zoomed in, now the analog digital converter, the ADC, is using this part of the screen, so you don't see the steps anymore. And you see how that frequency, it's kind of all over the place. That's why I think we had that blocky looking thing, because we're capturing a bunch of different cycles. See, if I freeze this now, if I do this, see how much better that looks? But all that messy stuff is because it's capturing so many waves at one time. You're seeing them all at one time in front of you, because it's like, you know, I forget what this one is, but 100,000, 200,000 waves per second. So it's capturing all those waves, and they're not all identical. They're not triggering exactly in the same spot. So we're seeing all kinds of stuff. So I think that's why the chunky part. But see, when we capture one, you can kind of see how the wave's not perfect. So Yeah, so if I turn it back on, we're seeing a whole bunch of waves all at one time. And then when I freeze it, you actually have to, it's put all those waves on top of each other. The last wave is the highlighted one. So you have to, and this goes with pretty much any scope I've used, you have to change the thing. So once you do that, it just keeps the last one and it gets rid of all the other windows or all the other pictures. So I thought that might be interesting for you. All right, guys, so there is the GW Instek. And see, it's right around 500 kilohertz, around 1 volt. And if I get a few more cycles on there, hope it's... I thought, it's still about the same. So I guess we got enough cycles to get a good measurement. So, okay, there we go. Okay, what I'm going to do is same thing. Stop this, okay? And then what we'll do is we'll increase this up to 10 millivolts per division. And then stretch it out. And look, there's our digital steps. There's 2 nanoseconds. Now, this is kind of interesting, right? Because instead of seeing that blocky thing, we're actually seeing, it's interesting how it did that. I'm not sure the difference in the GW. I don't know. It's kind of weird. I can't explain why it does it this way versus the way the Micsig did. This almost looks like it's oscillating between steps. But we took a step here, and the next step's up there, and the next step's right here. So that's 10 millivolts. If I drop it down, you'll get a... Well, if I drop it down, and if I bring this in, it might be more obvious. You can see the step, 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 step. So this is 20 millivolts per. It's like every 20 millivolts. It's the same as the Micsig, except for instead of seeing that just fuzzy block, we're seeing a nice clear sine wave, which that's interesting too. So just a different way they're capturing the data and showing it. Now what I did is I went to Acquire and I tried all 3 different, the peak detect, the average of 4, and I still got the same picture. So I thought that was interesting. Record length, it's maxed out at 10 meg. It doesn't have as many as the Micsig, but that's still quite a bit. So the deep memory's pretty darn good in this one. 10 meg is pretty darn good. The Micsig is just a little bit better. It had like 70 meg. I mean, that's ridiculous. This is 10 meg per, never gets divided unless there's certain things setups you do. The Micsig, it's 70. If you use 2 channels, it drops to 35. And if you use all 3 or 4 channels, it's down to 17. So it's still more than, it's not quite double this when you're using all 4 channels, but it's still better either way you look at it. But I don't understand this. So I tried changing different things, and I still got the same thing. I changed the memory actually. I went lower. Instead of 10 meg, I went less samples to see if it changed, and I still got pretty much the same picture every time. So, but anyway, as far as those analog digital steps, you can see them, chunk, chunk, chunk. So now if I start running this again, you'll see what you saw in the Micsig. Just a nice straight edge, because now the A to D, the analog digital converter, is using this whole screen and is dividing this up. Now, I can't go, if I could zoom in on that, then you can see the chunks again. So 8-bit scope. So 8-bit, same as the Micsig, 8-bit. All right, so now we're doing the OWON. And look at this, we're in 8-bit mode, length is 40 meg, so it also has a lot of samples. 500 millivolts per division, and right now 500 nanoseconds. That's a half microsecond, but whatever. Okay, so let's go ahead and freeze that one, okay? And let's stretch it out. And we can go to 10 millivolts again. Well, look at that, 8-bit scope. 10, 20 meg. Now this one's interesting. I kind of like this one better because it actually looks like an A to D should look. So, yeah, pretty interesting, right? So that's a really good picture. Oh, wait, hold on a second. Look at this, 8 bits. But hold on a sec. Let's go back half a volt. Let's go back to this window, turn it back on again, and look. What if we went to 12 bits? So now we're 12 bits. Let's freeze it. And let's stretch it out to 10 millivolts and drop this down to 2 nanoseconds. And look at that, nice and smooth. 12 bits, really smooth that thing out. All right, we're not done yet though. You guys know what we've got to do now. We got to try that 14-bit thing, right? So let's go back to half a volt. Stretch it back out again. Here, let's go right here. Whoops, I got to get it running so to let me change it. Okay, that's 14 bits. It's touch screen scope. It's like the Mixig, so try not to touch the screen because keep my fingers away from the focus button. All right, so let's freeze that and increase it to 10 millivolts again. Stretch it out, and of course we're going to see a smooth line. Man, it's even smoother. Look at that. Now that is the power of bits. An analog, so I don't know hardware-wise what this guy has in it. But anyway, it's capable of doing 14 bits. But I do want to point out one thing. Look at this length. It changed. At 14 bit, it went to 20 meg. So let me turn that on. And let's go there. Yep, drop to 20 meg. Now look, this is what it looks like when I run it. Look how smooth that looks. And that's just pretty amazing, right? You got all that vertical resolution. So even in this mode, 10 millivolts, 2 nanoseconds, it's still, I mean, those other ones were nice and smooth, but this still looks even a little nicer, doesn't it? So if I drop them down, there we go. By the way, all right, guys, we're here at the Picoscope 7, the new software. Now, here's that same signal. It's just a Class D amp running, and we're just seeing the noise from that at the output. So again, let's see. Okay, we got all these measurements down here from some other thing I was doing. So let's just clear them all. I could clear one at a time, but we got so many, I'm going to clear them all. And let's select the ones we want. We want this RMS, and we want frequency. And click over here, and so there we are, our 509 kilohertz and almost 1 volt. Let's get a few more cycles just to see if that makes a difference. 508, 990, not really, I don't think. Let's stretch it out and see if it changes. Yeah, if we got less than a cycle, it doesn't want to. So all we need is a couple of cycles to get a good reading. So that's good. And here's our trigger, and it has this thing from another setting. Let's go in here and turn off the advanced. I don't think we need that. We'll just go to simple trigger. Okay, there we are. Our simple trigger. Look at this, 8 bits. Okay, so we get a look at 8-bit scope. Okay, now, in case you're not familiar with the Pico, the channels are right here. Channel A is the only one I have turned on. It goes from plus to minus 2 volts. So 2 volts up here, minus 2 volts here. So a 4 volt spread across these 10 divisions. Okay, and up here's our time base, 500 nanoseconds per division. And we have our trigger. You know what? I want to stop in here for just a moment. I want to check this out. I want to see if we have these maxed out. We kind of do. Yep, 10 gigasamples. Okay, we got those maxed out. It'll automatically set what we need right up here based on these other things. See these waveforms? It saves a bunch of waveforms. That takes some memory, so I'm going to lower that to, say, 10. I could go to 1, but anyway, there's 10. So I'm going to get rid of them. Okay, this just saves. Oops, did it save it? Let's see. We got to start running it. and then it was still saved the last 30, so that's what the problem was. So now if I hit the 10, it just pulls up 10 waveforms, the last 10 waveforms. Okay, we're going to get rid of this guy. And that takes less memory. I don't know if it improved this over here. That's okay. We got enough. So let's go to this magnifying glass, and here's the window, what we're looking at up here. Okay, now I'm going to zoom in on this where the trigger is right here, put a box around that. Okay, there we go. Now I want to zoom in on this a little bit more and the vertical as much as I can. And I'll click on this one more time, and I'm going to move this guy up here. Love how you can move these things around. Okay, and what I want to do is I'm going to stop this for a moment, and there's our 8-bit staircase kind of thing going on. So let's take these cursors, let's drop one down on that shelf, and then let's go one below it. Okay, so that's showing 18.9 millivolts up here. I can move this over, line it up with this window if I want, and then I'll take these cursors, and I want to see what the time is for each one of these little shelf things. Now that's a skinny shelf I grabbed, and that shows about 1 nanosecond. Let's go on these fatter ones. And that's because my sample rate's so high that I think I'm oversampling. So that's why some are short, some are what we might think standard size, 4 nanoseconds. So about 19 millivolts and 4 nanoseconds. And this is our complete waveform in this window it's showing us, and this is the part we're zoomed in. Okay, now check this out. I'll get running again, and I'll go up to hardware bits, and let's change it to 12. Okay, now I'll freeze that. Look at that, nice and smooth again. So there we go. Now check this out. My samples and this stuff changed up here a little bit when I went to 12. I'm going to drop back down to 8. I'm going to show you something else you can do with this Pico. You can go per channel and change each channel separately. So here's my probe I have set up, the DSP. See, I can filter here too separately. I don't have any filters going on right now, 20 meg or any otherwise. See, the 20 meg would be right here. And then per channel, I can also do this change this filter, whatever I want. But also I can do this and go this resolution enhancement and go by half bits. Look at that. So 9 bits, it's starting to look pretty good. Yeah, 9.5 bits, that's looking pretty smooth. I'll stop it. It's pretty smooth, right? So we have both these options we can use on the Pico. And, you know, I can go up higher if I want. You know what? Let me go back to 8 here. Okay, guys, so what I want to show you is I can also go up here and I can go 9-bit, or whoa, 12. And I can go again, 14. Check it out. 15. And even up to 16. That's pretty crazy, right? So what I'm going to do, whoops, and if you make a mistake like that, you can just hit this undo button. I'm going to grab this and pull it down, and I'm going to actually turn off the zoom and just zoom out. And there's our waveform. So it's pretty darn cool, right? Just wanted to show you that with the Picoscope. And again, we can get rid of this too, I guess. Get rid of the cursor since can't really see them there. But yeah, that's the power of this little zoom thing. You can zoom in on top of the waveform, and right now it's looking pretty good, right? Pretty smooth. You can also average if you want, but that's another way to kind of average out things. But if I drop this back down, start seeing a little bit of chunky stuff. 12 bits. Look at that. Still sharp though. It's not staircasey too much, but it's, you know, let's go down to back to 8, and there's that staircasey on top. So see here, if you look at our zoom window right here, we're looking at the top of this waveform right up here. And it gives you the magnification right here in the left corner, but we can use our little things. But anyway, yeah, I just wanted to show you that. Different ways to do it. Alright guys, so what do you think? It's pretty cool, huh? I don't know why. So 8 bits, I've been around for a long time. Pretty much all scopes, you know, up until you get a few $1,000s before they go to 10 bits and that. A lot of people I just don't think are looking for that because they're worried about, you know, capturing that waveform, you know, the digital thing. Well, the scopes have come a long ways. They're doing that. But now we want to improve on that vertical thing, right? We want to get the resolution there too. So we got to start pushing these scope companies to give us 10 bits at least. 10 bits is 4x better than 8 bits. It's not the cost of the A to D chip. Yeah, sure, they're going to cost a little bit more, but what if the chip costs, you know, a little bit more, $5 more? What if it did? That's nothing for the cost of the scope, right? The real cost comes in the low noise circuits at the input, because when you're going down to less than 40 millivolts, let's say you're 10 bits and you're going down to 9.8 millivolts, that 9.8 millivolt step, that first step might be covered in noise. So maybe it's you have to get a 12-bit A to D and have a really clean input to get 10-bit usable. And the way some of these scopes, like this Pico, can go to 8-bit hardware A to D to up to 16-bit, they just sample extra times, and they sample extra, you know, different spots each time, so they kind of fill in those steps. So that's why you get a fat step, a thin step, fat, you know, that's why you see stuff like that. At least that's what I believe how it works. Okay, so that works best when you have repeating waveforms. If you have a transient that just happens, yeah, it's not going to, you know, work as well on that. If you have a transient that happens, you're expecting that, you might trigger and really zoom in on it so you're filling that transient in the whole screen, so it's not going to be an issue. Where this vertical thing becomes an issue is where you're trying to see, you know, the whole signal, but then you want to zoom in on sections. Like you want to zoom in on the top of it, you want to zoom in on the crossing point or the bottom of it. You know, you want to zoom in on a section, you want to have that resolution. That's where that counts. So I feel like today they should all be 10 bits. So what do you think? That's why the Picoscopes are so awesome, because the software continues to develop. Even if the hardware is fixed, the software takes care of it, and you know, it looks awesome, right? Now I have the 4444 that comes in hardware at 12 bits. That OWON, I'm not really sure what the hardware portion of that is versus software. I'm not really sure. So, but I think it is better than 8 bits though. So I think it is 12 or 14 bit. I think it's 12 bits, but I don't know. I'm not sure. I could probably figure it out by investigating, looking at the signals. I don't know. Anyway, what do you guys think? 2 thumbs up to my patrons. 2 thumbs up to OWON, Mixig, GW, Pico. I bought the GW, and this Mixig, I bought my first one, but this one they gave me. So, but I am a fan of these scopes. Today, if you want to know what I'd choose, I need to do a video on that, right? Okay, so thanks for watching, guys. I'm trying to think, something's on my mind I want to tell you guys about. But anyway, I got a bunch of projects backed up. I got so many videos backed up right now. I'm going to start cranking some videos out. I'm going to be gone for a few days. I got a trip that I got to go on, but I'm going to try to put out a couple videos, this being one. And so thanks for watching. Really appreciate you guys. Thanks to my patrons. Really appreciate those guys. I'm going to start putting a list of patrons on my video, and I've been waiting for everybody to respond whether they want me to show the names. Some guys don't want me to show their names. I don't have a lot of patrons, so the ones I do have, I really want to, you know, give them props, you know, for being such great guys and supporting me. And I really appreciate you guys that hit the super thanks button. That happens every so often, and I really appreciate that. So like the video. It's a free way to support the channel. I'll put links to these scopes down here and, you know, down in the description, and using those links is a free way to support the channel too. I get a little bit and it doesn't cost you anything extra. Thanks for watching, guys. Have a great weekend, and we'll catch you next time.